Welcome to AS Chemistry. We're looking at different formulae today. You'll have come across some of these before at GCSE, but at A-level we use a few different formulae that are going to be unfamiliar to you, and I want to take you through the different types and why we use them today. This is ethanol. It's the alcohol you find in alcoholic drinks, and if you remember your GCSE, you'll know that we have two carbon atoms, which I've drawn in black here. We have 6 hydrogen atoms, which are in white, and I've got one red oxygen atom. And at GCSE, the formula that you'll have seen used probably quite a lot is a molecular formula. A molecular formula is a formula that you will have used lots of times, and its definition is it's a formula that shows the number and type of atoms of each element present in the molecule. So there are two things with a molecular formula that we need to see. The first one is the number of atoms, and the second one is the type of each. And how we're going to do that here is we're going to go, right, okay, well, if we look at this molecule, we have two black carbon atoms, and we're going to start with C, because it's organic chemistry, carbon comes first. And we have two of them. So subscript, as you did at GCSE, we're going to put a C2. Now, we also need to show our hydrogens. We have 6 of them. And it's important with a molecular formula, if you're asked at AS level or A2 level, to make sure that you put all of those together. Otherwise, it's not really a molecular formula. We're going with C2H6 and then just one O at the end, and this is a convention which you should use. Carbon first, then hydrogen, then oxygen is the normal way to do it in organic chemistry, followed by anything else which is in the molecule. So from my molecular formula, I know the number of atoms. I have 2 of carbon, 6 of hydrogen, 1 of oxygen, and I know that there is carbon, hydrogen and oxygen atoms there. Nice and simple. So the next type of formula is an empirical formula. An empirical formula is a formula that shows the simplest whole number ratio of atoms of each element present in a compound. So what we're going to do to work that out is we're going to look at either our picture or our 3D image, or we can look at any other type of formula that we've got, and we can go, right, okay, well, what's the simplest ratio that we have? And here, in this case, we can see that actually, if we take C2H6O, we can't make a simpler way of putting that. We can't say, well, if we have half the carbons, we'll have C, and then we have half the hydrogens, we'll have 3 of them, and if we have the half the oxygens, we'll have a half, because the definition says it's a whole number ratio. This is the simplest whole number ratio we can have for this chemical, so therefore we can have C2H6O is also the empirical formula. So why would we have an empirical formula? Well, an empirical formula is usually the first thing we know about an unknown chemical. We can do all sorts of analysis on a chemical, but the most useful thing is to work out, well, what is the ratio of carbon to hydrogen to oxygen? And if we know that, we can then use mass spectrometry to work out how many times that ratio is repeated, and therefore work out how the total formula of the chemical. So this is usually our starting point, and from it we usually work out the molecular formula, which is the one that you're used to seeing. So the next type of formula that we come across is a structural formula. And a structural formula we're going to define as a formula showing the minimal detail for the arrangement of atoms in a molecule. Now, it's all very well as saying, well, it's C2H6O, but does the O go here? Well, it does, because it's ethanol, but we could actually put that oxygen in between these two carbon atoms, and the molecular formula would be the same. So we need a formula which actually shows us where these atoms are arranged. Otherwise, we'd have to draw it out every time. And a structural formula, you basically need to start at one end of the molecule, and you need to write down for each carbon atom what is on that carbon atom. So we're going to start here on this carbon atom here, and we have a carbon, and joined to this carbon atom we have 3 hydrogens. So we're going to say the structural formula starts with a C and attached to 3 hydrogens, CH3. The next carbon atom along has 2 hydrogen atoms and an oxygen. And joined to that oxygen is a hydrogen. So we end up with a structural formula, CH3, CH2, OH. We haven't shown any bonds, it's the minimal detail. We haven't had to draw anything out, which makes it nice and quick to write. We have shown the arrangement of the atoms in the molecule, and that's really useful. So the next type of formula is a bit like structural formula, but it shows us a bit more detail. The structural formula showed us the minimal detail about where the atoms were. Now we want to know about where the bonds are, because as you're probably aware from GCSE, sometimes we have double bonds and sometimes we have single bonds, and we can have triple bonds as well. So I want to show where the bonds are, and this 3D model is basically what we're trying to replicate here. This is something that you will have seen probably at GCSE when drawing alkanes and maybe even ethanol itself, and it's called a displayed formula. Now it's very important for your AS not to be lazy here, because the definition we're using is that it's a formula that shows the relative positioning of all the atoms in a molecule and the bonds between them. What a lot of people get into the habit of doing, because that's how they've seen it at GCSE, is by clumping some of these atoms together. But we don't want to do that. We want to show all of the bonds. So we're going to put a C for the carbon atom there. And usually you draw these with kind of like in a nice organised 90-degree sort of shape. That's not how they are in reality. The bonds here are actually 109.5 degrees apart. We're going to show it like this, just for simplicity's sake. We're not interested in exactly where these atoms are. We are more interested in showing clearly what atoms are bonded where and by what type of bond. So we have 3 hydrogens here surrounding this carbon, 3 single bonds there, a single bond between the 2 carbons there. We have a hydrogen there, we have a hydrogen there. Now actually it doesn't matter whether that hydrogen goes there or here, as long as we've got the correct atoms bonded to each other, the O and the H, then it doesn't matter. As long as this matches this structure, it's fine. So this displayed formula, you'll see I have drawn the bond between the O and the H. Lots of people miss that out when drawing ethanol, and it's important that you put it in there. Last definition, and it's quite a large one, is for a skeletal formula, and a skeletal formula is a simplified organic formula with the hydrogen atoms removed from alkyl chains, leaving just a carbon skeleton and associated functional groups. That's a big definition to remember, and what it means is basically when I come to draw this, what I'm going to try and do is I'm going to try and simplify it so that basically drawing big molecules doesn't take forever. If you had something like icosane, you'd have C20H42. You'd have to draw all of the bonds, all of the hydrogens, It's much quicker to draw a skeletal formula, and that's why we like them. So what I'm going to do is I'm going to ignore these 3 hydrogens here. We're going to look at the skeletal formula and we're going to go, right, we're going to assume that they're there. So we're going to start with this carbon atom, and that's just going to be a point here. That's all. And then the next carbon atom is also going to be a point. And then in between them is a single bond. And that's what it's going to look like. You don't even need to exaggerate these points, it can just be a single line to represent the bond. And what we're assuming here is there is a carbon atom on this point and a carbon atom on this point. And because we can't see anything else here, we assume, right, carbon has 4 bonds, there's one of them, there must be 1, 2, 3 other bonds, there's nothing written there, it must be hydrogen left over. Here, we're going to make another single bond this time, and we're going to go to another point. We're going to ignore these 2 hydrogens again, but this time we have an oxygen there. The definition says that it's going to leave just a carbon skeleton, that's this bit, and associated functional groups. Now the ethanol, this is the functional group. This is the thing which causes ethanol to have the chemistry that it does. And so the oxygen and the hydrogen we are going to leave there, like that. So you can see I've just taken off the hydrogens and simplified the carbons so that they are points. Because these bond angles are 109.5 degrees. You'll see most skeletal formulas done as sort of zigzags for carbon chains to represent that kind of bond angle, and there'll be more on bond angles later in the course. So here's an alkane you should recognise. I've chosen this one because it has a slightly clearer definition of what an empirical formula is, but also it doesn't actually have any functional groups. So what does that look like with a skeletal formula? So we'll go again from the top. Molecular formula: 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and that's it. But this time, when we come to do the empirical formula, we're going to see actually 4 and 10 both divide by 2. So we can have C2, because 4 divided by 2 is 2, and H, now 10 divided by 2 is 5, is the empirical formula, because that is the simplest ratio. It doesn't simplify any more. 2 doesn't go into 5, 5 doesn't go into 2, so this is the simplest whole number ratio we can have. And you see this time it is different from the molecular formula. Structural formula. Now this time I'm going to abbreviate this again, because we try to look for the minimum detail. Here we're going to start over here, so we have CH3, and then I'm going to have a CH2, then I'm going to have another CH2 here. Look, CH3, CH2, CH2. So what I'm going to do is I'm going to say, right, well, let's abbreviate that. Let's say that there are 2 CH2 groups in the middle, and then we're going to say CH3 on the end. Okay, now I've left the 2 ends as they are because I want to show that this carbon is joined to the repeating bit of CH2s, and I want to show that on the other end of this repeating bit is the same. And if I just had that there and then put it in brackets and a 2, that might be a bit ambiguous. Okay, so I'm going to show both ends, and the middle I'm going to shorten. The displayed formula is going to be a carbon, 3 hydrogens surrounding the carbon, carbon, 2 hydrogens surrounding the carbon, carbon, 2 hydrogens surrounding the carbon, carbon, 3 hydrogens surrounding the carbon, as you did at GCSE, no problem. And the skeletal formula here, there are no functional groups, so we're going to abbreviate the whole thing. We're going to simplify it down, ignore these 3, those 2, those 2, those 3 hydrogens there. We're just going to go with the carbon atoms, 4 in a line, 1 here, up to there. Then we're going to go down to here in a zigzag to show that it's 109.5 degree bond angle. Then we're going to go up again, and it will still be the same bond angle, so we'll end up with a wiggly line which looks like that, and that is literally it. And that makes drawing really long hydrocarbon chains really, really simple, because you can just zigzag them until you have the correct number of points.